our example has two samples, that is the pilots versus the members of the general public, and one variable, yes or no to the question. So our chi-squared test is going to test the null hypothesis that the distributions are the same for pilots versus public versus the alternative that the distributions are not the same. Or, since we only have a yes or a no variable, a variable with only two categories, we can write this simply as the null hypothesis that the probability of saying yes given that you're a pilot equals the probability of saying yes given that you're a general member of the public versus the alternative that those probabilities are not equal. Now, how are those two null hypotheses the same? How is the probability of saying yes given that you're a pilot equaling the probability of yes given that you're public equivalent to the null hypothesis that the distributions are the same for pilots versus public? Well, if you know that the probability of saying yes given you're a pilot equals the probability of saying yes given you're public, then you automatically know that the probability of saying no given that you're a pilot equals the probability of saying no given that you're from the public. So those null hypotheses are in fact the same. Since we only have two categories, yes or no, defining the probability of saying yes automatically defines the probability of saying no. So if we let P1 denote the probability of saying yes given that you're from group 1 and P2 denote the probability of saying yes given that you're from group 2, and we want to test the null hypothesis that these two probabilities are equal against some alternative, we're going to introduce the Pearson's chi-squared test statistic. Pearson's chi-squared statistic tells you to take the observed value for each cell, that's these O's, minus the expected value in each cell, that's the E, squared, and then divided by the expected value for that cell. Do that calculation for each cell, and then sum those calculations all up. Now, we have the observed values, the O's, that's the data that we collected. That's the data in the table. But how do we calculate those E's, those expected values? Well, remember, when we're conducting a hypothesis test, we assume that the null hypothesis is true. If the null hypothesis were true for us, then the probability of saying yes, given that you're from group 1, in this case the pilots, equals the probability of saying yes, given that you're from group 2, that you're a member of the general public. So P1 would equal P2. And since P hat 1, that is the sample proportion saying yes from group 1, and P hat 2, the sample proportion saying yes from group 2, those would be estimating a common population proportion. The probability of success would be the same under group 1 or group 2 in our example. And we could estimate this common P by using a weighted, or sometimes called a pooled estimator. So we would take the sample size for group 1 times the P hat for that group, the probability of saying yes, and the proportion of saying yes, and the sample size for group 2 times the P hat 2, and then add those up and divide by the total sample size, N1 plus N2. Now what is P hat 1? That's just Y1 over N1, the number of yeses from group 1 divided by the sample size from group 1. And what's P hat 2? Y2 over N2, the number of yeses from group 2 divided by the sample size from that group. And so if we just fill in those P hats, we can cancel the N1 and N1 and the N2 and N2, and we end up with just Y1 plus Y2 over N1 plus N2. Now what's Y1 plus Y2? That's just our total number of yeses across both groups. And what's N1 plus N2? The total sample size across both groups. So the pooled estimator of the overall proportion of saying yes makes sense. It's just the total number of yeses ignoring the groups divided by the total sample size ignoring the groups. Now a little sidebar. Suppose you're flipping an unfair coin where the probability of a heads is 0.3 and the probability of a tails is 0.7. How many heads would you expect to see if you were to flip this unfair coin 10 times? All right, if the probability of a heads is 0.3 and you're flipping it 10 times, I'm sure you were all thinking that you'd expect to see 10 heads. And that's right. I mean, you're expecting to see 3 heads, excuse me, because 0.3 of the 10 would be heads. So 3 heads. But if you pay attention and recall, that's actually the binomial expected value. That's the number of coin flips, 10, your n, times your p. The probability of a success in this case is 0.3. All right, so if we can apply this thought process, we can get the expected number of successes for group 1. Well, our n, our sample size, is the sample size from group 1, n1. And what's the probability of a success? That's our pooled estimator, n1 times p pool. And compute the expected successes for group 2. We'd have n2 times p pool. And now we can figure out how to get our expected values for each of the cells in our table. All right, so a success, which was called yes in our example, and a failure, which was called no. We have our group 1, which in our example was pilots, and group 2 was members of the general public. Okay, but in general, we would call that row factor success and a failure, and the columns the different samples. So how many successes do we expect for group 1? How many yeses do we expect? We just said that. That's the sample size for group 1 times that pooled probability. And we calculated that to be y1 plus y2 over n1 plus n2. Good. And the same logic would apply for group 2. We would expect n2 times the probability, which is y1 plus y2 over n1 plus n2. All right, good. Now, if the probability of a success is n1, or if the number of successes, excuse me, is n1 times y1 plus y2 over n1 plus n2, and we expect that many successes, that many to say yes, how many do we expect to say no? How many failures do we expect? Well, if our total sample size for group 1 is n1, our total sample size for group 2 is n2, we can figure out how many failures we expect in group 1. It should just be the sample size minus the expected number of successes. And that'll give us the expected number of failures. So let's do it. So we have n1 total sample size for group 1 minus the expected number of successes, which we have right in that first cell, n1 times y1 plus y2 over n1 plus n2. Looks kind of ugly, but not really a big deal when you just think about it for a second. And so I'm going to rearrange this just so I can illustrate something in just a second. This would be fine to fill in for your expected number of failures. That would be great. It's correct. But I want to put it in a little bit different of a grouping so you can see a pattern. You'll see why we're doing this. All right, so I'm going to factor out the n1. I have an n1 on both of my terms. So my first term becomes a 1, and my second term just becomes y1 plus y2 over n1 plus n2. And I could go on one more time. I could get a common denominator for this stuff inside my parentheses. And I think I'll just bring this up here. So I'm going to bring my n1, just keep it the same. But inside my parentheses, instead of that 1, I'm going to get a common denominator. So that 1 can be written as n1 plus n2 over n1 plus n2. So we have a common denominator with our second term, which is y1 plus y2 over n1 plus n2. And we have a common denominator, so that ends up being n1 plus n2 minus y1 plus y2 all over n1 plus n2. And one last time, I'm going to rearrange terms. I have n1, and then in my parentheses, I'm just going to reorganize the terms in my numerator. I'm going to make it n1 minus y1 plus n2 minus y2 all over n1 plus n2. And I'm going to write this expected number of failures in that way in my table, and you'll see why in a second. So this one's going to be n1 times n1 minus y1 plus n2 minus y2 all over n1 plus n2. And using the same logic, we would have n2 times that same stuff over here. So minus y1 plus n2 minus y2 all over n1 plus n2. All right. So I am going to erase this. You have more room on your paper, but I'd have to switch slides and rewrite all my expected counts again. So I'm just going to erase this so I have a little bit more room to write and my screen is not so cluttered. So now, we had N1 people in group 1, N2 in group 2. How many total successes do we have? Well, how many total number expected successes do we have? We could add these, the number of expected successes, the ones for group 1 and the ones for group 2. If we add them together, N1 times Y1 plus Y2 over N1 plus N2, that's my expected number of successes for group 1, plus my expected number of successes for group 2, which is N2 times that same stuff. And this is the same as this, so I can combine terms again, and I'll get N1 plus N2 times that same stuff. And look what happens. N1 plus N2 cancels with N1 plus N2, and I'm left with Y1 plus Y2. And the same thing is going to happen down here on my expected number of failures. I'm going to end up getting N1 minus Y1 plus N2 minus Y2. And if I add up my total sample size, if I add up my column totals, I get N1 plus N2. And if I also add up my row totals, these total expected number of successes and expected number of failures, notice that I again get N1 plus N2. So I get Y1 minus Y1, Y2 minus Y2, and then I'm just left with the N1 plus N2. All right, so why did we go through all of this? Well, you're going to see in just a second. Go ahead and erase this again. I need to figure out how to get a bigger eraser. All right, how can we calculate those expected counts in a more simple way? Well, take a look at what we have discovered. The expected number of successes for group 1 is N1. That's right here. That's your column total. Times Y1 plus Y2. Look here. That's your row total for the row it's in. Divided by N1 plus N2. That's your total. All right, let's do the expected number of successes for group 2. So right here. Well, we've got N2, which is the column total for the column that's in, times Y1 plus Y2, which is the row total for the row it's in, divided by the total. And hopefully now you see the pattern. Let's do it for the expected number of failures for group 1. N1 is the column total for the column that's in, that cell is in, times N1 minus Y1 plus N2 minus Y2. That's the row total for the row that cell is in, divided by N1 plus N2, your total. So the way that you're going to get each expected count is going to be to take row total times column total divided by what I call total, or table total. All right, and that is going to be the ticket to calculating your expected values. Row total times column total divided by total total. Very good. Now we're ready for an example.